So in this tutorial we'll talk about practical buck converter and its output equations, current ripple, voltage ripple with the output capacitor, output filter capacitor across the resistance. So the circuit we are talking about is this. We have this diode, inductor. Why we are placing this inductor? We are placing this inductor in order to filter the switching components, and we are expecting a very nice DC output voltage across this load resistance, right? So this we are calling as V. um, let us say it is small v of t, right? Small v of t, yeah. And this is inductor current IL. So since the filter capacitor is in parallel, V of t is nothing but the voltage across the capacitor. We have discussed small ripple approximation and switching circuit, um, switching cycle averaging, right? Switching cycle averaging. Let's recall what is small ripple approximation. We can replace the continuous variables like IL and voltage across the capacitor with a DC component plus some small ripple which can be approximated to 0, right? So this switching ripple, this ripple voltages on the voltage the ripple current and the ripple voltages can be ignored and do the analysis as we have done previously. So, and what about this switching cycle average? The average inductor voltage over a switching cycle is equal to 0, and the average inductor current over a switching cycle is equal to 0. So these are the two fundamental principles that we rely on and then compute our output equations, current ripple, voltage ripple expressions. So we have already seen that the output voltage we are expecting it to be V of t, small v of t is equal to capital V plus some V ripple, and we are approximating it as capital V. So to get the feel of this, let us see a actual circuit, whether this particular approximation is correct or not. If it is correct, in which case it is correct, if it is not, in which case it is not. Because this particular approximation, when we do, we are saying essentially this node voltage is almost constant, even though there is switch on and switch off, right? Then we are actually ignoring the dynamics of this capacitor in the first place, right? So we'll see whether it is reasonable or not through a simulation. So if you see in here, I have a capacitance of 8.85 microfarad and an inductance of 200 microhenry. The voltage, the output voltage across the 4 ohm resistor is varying between 6.25 to 5.8, and the average value is around 6 volts, right? So in this case, the voltage at the node, at the output node, is can be loosely approximated to 6 volts, and see how the inductor current varies, right? So let's go ahead and try to finish this output voltage equation with filter capacitance in place. Basically, I have placed in filter capacitance, but it is not showing up in our equations. So let's try to derive it. So inductor voltage, which is inductor voltage VL when switch is turned on, is equal to Vg minus output voltage with SRA, right? And when it is turned off, it is just equal to minus V. And we have already told that the average inductor voltage or a switching period is equal to 0. So let me average it in the turn on. Vg minus V plus 1 minus T Ts into minus V whole divided by Ts is equal to 0. So then what we end up with, if we simplify that equation, we'll get V is equal to D into Vg, right? And similarly, when the voltage is constant, when the output voltage is constant, what will be our inductor current? So the equation for inductor is LdILd by dt is equal to the voltage across inductor, right? So this particular voltage, uh, how do we write this? So during turn on, we can say that it is Vg minus capital V. So dIL by dt, or I want to find the expression for inductor current, then it should be Vg minus V divided by L into T. Since this is constant, and I of T is equal to this during 0 less than T less than T on, right? So we have this inductor current rising with this slope, when it is turned on. So it is rising with a slope of Vg minus V by L. When the inductor is turned off, what is the equation? The equation is just Vg goes to 0 since the diode is in conduction now. So I of t will be equal to minus V by L into t. So this particular slope, actually this should be t minus t on, right? If we are considering as 0, this should be t minus t on. So it is falling with a slope of V by L. And now what is the average value for this inductor current? It is nothing but the average of these two terms, right? Or the same average, as we can see the circuit here. This is our circuit, right? So this is I L of t which we are talking about, and it has a component of DC and a ripple. So the ripple current should be passing through the capacitor and the DC current should be passing through the resistance. Why? Because capacitor acts as a open circuit for DC currents, right? So whatever current that flows in this resistance is nothing but output voltage divided by R, and it is equal to the average value of inductor current over averaged over a period of switching cycle, right? So now there is a ripple current, right? There is a ripple current entering into the capacitor. Then if there is a ripple current, then there will be a ripple voltage riding on, right? So now let us try to find out that ripple voltage, how it would look like. So the sort of current that is passing into inductor is this, and this is my averaged voltage. So when I subtract the average voltage from the actual current, then I will end up in a ripple current just like this, right? This is 0, this is delta I, or ripple current is what I'm calling. So we know this equation that 1 by c integral I dt is equal to voltage in capacitor. So this is the sort of current that is entering, and since we are having switching frequency far greater than the oscillations that come in this second order circuit, that means I'm calling it as damping frequency. So usually when we switch this circuit, let us say I have switched this circuit, what could be the response? It could be a damped sinusoidal waveform of certain frequency, and our switching frequency is far greater than this damped oscillation. So we are seeing a linear rise, and linear fall of the current rather than some sort of sinusoidal nature. Now, since it is linear and centered at this point, we expect the integration. We can write it as some t minus d, right? It is linear. So when I integrate it, I will see some sort of parabolic nature in the capacitor output voltage. So this is the ripple that is riding on the capacitor. How can we find the expression for capacitor voltage? Is by this way. Now we can write down capacitance is equal to Q by V. Now that is equal to, so we can write this Q with this or we can write it as delta Q by delta V, right? If the capacitance is linear, the dynamic capacitance is equal to the static capacitance. So this is the dynamic capacitance we are talking about, and we know that this is equal to the capacitance. What is our objective? Our objective is to find ripple voltage, that is equal to delta Q by C. And if we integrate this current, we end up in charge, right? There is some charge at every cycle, but it is also to be noted that the summation of this charge is going to be 0, since we have already mentioned the average capacitor current over a period, switching period, is equal to 0, right? So how do we find out this delta Q? That delta Q is nothing but the area, right? So this is the triangle, and we need to find out the area of this particular triangle. So the area is equal to half into the ripple current magnitude. This is delta I. We already know the expressions for delta I. So half into delta IL into, how much is this period? This is Ts by 2 into Ts by 2. So divided by C. Now what is delta IL? Delta IL is equal to, we have already derived this expression in the previous video tutorial, or we can derive it once again as well. So how do we calculate this delta IL? What I am talking about delta IL is this portion is delta IL. So this is the difference between the minima and maxima. That is, we already know that IL is equal to Imax. Let us find out Imax. Okay, we'll do this again. Imax is equal to average current IL plus delta IL. Imin is equal to average current IL minus delta IL. Right? So what is Imax? Imax is nothing but Vg minus output voltage by L into dTs, right? Isn't it? We have wrote down that expression right here, right? So when I place dTs, that will be equal to the change in current, right? Plus this should be plus I min. Why? Because it is starting from I minimum, and with this slope of Vg minus V by L, it is going to an Imax. So what is this relation? Imax is equal to this particular raise plus I min. So what do you want here? Imax minus I min by 2, which is equal to delta IL, that is equal to Vg minus V by L into dTs by 2. So let's substitute this equation in here. Now what do we get? Delta V is equal to 1 by 2. There are two 1 by 2s, three 1 by 2s, so it should be 1 by 8 Vg minus V by L into Ts by 2, T square S by 2 into D. Sorry, we have considered already 2. So this is the expression. When we just try to simplify it, we'll get at IL into R into Ts into 1 minus T by 2L to 8C. We are just substituting V is equal to D into Vj by R. Sorry, yeah, V is equal to, or we can substitute, there can be, but this is the main equation. You can just substitute what is V, or you can replace Vg, you can express it in V, output voltage. So this is the equation that we are looking at. Now let's see something more interesting. So in a practical buck converter, we will have, let's come one by one. We will have a diode and an inductor. Let's see if we add the capacitive, the ESR of the capacitance, and see what will be its effect. Will it have any significant effect? Yes, it should be, but we have not considered that resistance while we are calculating this particular wave shape. If it is resistance, then let's see what happens. We have this sort of ripple riding on the ripple current that is going onto the capacitor. If we have a resistance, we will have a resistive drop which is of the same nature, and capacitive drop which is of this quadratic nature. So the output voltage ripple now will be the summation of these two, which comes out to be, it is difficult to draw, I'll just try to show it in the simulation. So in our simulation now I have a capacitance of 8.85 microfarad and a resistance of 140 milliohm. Let me change that to some higher value. You can see the change in shape of the green waveform. First of all, the ripple voltage has been increased since the drop has been increased, and it is moving closer towards a triangular shape rather than a parabolic shape. If we try to reduce the resistance, it is more closer to parabolic nature. So that is the end of this video.